Welcome back to our new video. In this video actually we will discuss about the diffusion in the solids. Okay, as you may have studied this in your higher secondary schools and all about the diffusion. Okay, now let us see how within the materials the diffusion may happen. Okay, materials. Okay, in general all types of materials often heat treated to improve their properties. We all know that. Okay, if we like in placing these material or the metals in some elevated temperatures, and we will add some alloys, okay, or like we will apply some amount of force or beating to improve its strength and many other properties. So all the materials in general is subjected to heat treatment. Heat treatment is a important technique used in these materials. So the phenomena that occur during a heat treatment like almost always involve atomic diffusion. Whenever a substance is subjected to heat, okay, the atoms within that material will absorb a certain amount of energy, and it will move from a higher concentration area to a low concentration area. Okay, it is a general tendency. Okay. Often an enhancement of diffusion rate is desired, on occasions measured as a rate to reduce it. And heat treatment temperatures and time. Okay, these are the two important factors which depend: temperature and the time. Or the cooling rates are often predictable using the mathematics of diffusion and appropriate diffusion constants. Okay, so for these things, actually the two important parameters are the temperature and the time. Okay, and this cooling rate can be calculated with the help of certain mathematical equation. So this is an object like it composed of different elements. So this is a light blue elements, and this is a dark blue some other elements, and red is another element. And we can see that when heat is applied to this zone, both the elements from their higher concentration regions, they will move towards the other lower concentration areas. Okay, this light blue or this green colored atoms will diffuse into this one, and similarly this will also diffuse into this material. Okay, so the diffusion is an important thing which should be studied. And next is the we can define diffusion as a stepwise migration of atoms from the lattice sides from one lattice side to another lattice side. And the interdiffusion or impurity diffusion, it is classified into two. That's first one is impurity diffusion. Actually here initially there will be two material, and what will happen is that when the temperature is increased, the diffusion is of the copper into this nickel will happen, and similarly the nickel will also diffuse into the copper. So as the time progresses, the concentration profile will look like this. Okay, initially it was like this, and as the time progresses it will look like this. And the self diffusion which is happening for the pure metals, here all the molecules will be same, but they will exchange their position among each other. Okay. So now let us discuss with the diffusion mechanism. In fact, the atoms in the solid materials are in constant motion, rapidly changing. So there are certain mechanisms we can say, like two factors which two conditions that should affect the movement of an atom is: first one is the empty adjacent space, and next one is the atom needs sufficient energy to break the bonds. That means it need to need energy to break the nearby bonds or it's from its neighbors, and it also need another adjacent space for them to move. Okay, actually these are the two conditions which are needed. So this diffusion is basically based on the atomic motion. Two models were developed. Okay, the first one is known as vacancy diffusion, and second is an interstitial diffusion. Let us see one by one each. Okay, then first one is the vacancy diffusion. I think in this one there is a vacancy will be there in the nearby area, and what will happen is that the atom, when it get the sufficient energy, it will move to that nearby vacancy. Okay, and one of the important factors which depend is the number of these defects or number of these vacancy. This diffusion directly depends on the number of the defects. So if the concentration of the vacancies are higher and if elevated temperature, this diffusion will happen. Okay, so next one is the interstitial diffusion. So interstitial diffusion happens when one atom or the impurity atom, what I will say, it will be very much smaller, should be very much smaller, and it should pass between two atoms, and it will move to the nearby space. And the condition is that it should be very much, or it should be small enough to fit to these interstitial positions. In most alloys, this interstitial diffusion occurs much more rapidly than diffusion by the vacancy mode, which we have discussed earlier. Okay, since the reason is that the interstitial atoms are smaller and more mobile, and it can easily move within the through these interstitial spaces. Okay, and anyway, we can see that there will be more interstitial positions than the vacancy, so we can easily say that it can easily transfer through these positions. Okay, so that's the one thing. And there is let us see some mathematics regarding this one. First one, we will see a steady state diffusion. A steady state diffusion is a time dependent process. Okay, and diffusion rate can be expressed with the help of a factor known as diffusion flux, which is termed as J. Okay, and another thing is like the mass or the number of atoms, which is represented by M, and the cross-sectional area through which it travels, that is A, and the solids per unit time. Okay, area, and per unit time, T is the amount of the time required to transfer those atoms. So it can be represented by J is equal to M by AT, and like in terms of the time or in differential form, this J can be represented again like 1 by A into dm by dt with the number of atoms or the mass of the atom crossing per unit area at a unit time. So the units can be of J can be represented by kilogram per meter square second or atoms per meter square second. Okay, so this is a thing. And now let us see the how it works out. Okay, if the diffusion flux does not change with the time, we will call such a process as a steady state diffusion. Okay, so steady state diffusion, as we have discussed earlier, is a thing or the diffusion flux which has no change with respect to the time. Okay, steady state diffusion is the diffusion of atoms of gases through a plate of metal for which the concentration or the pressures of the diffusing species of both surfaces of the plate are held constant. But throughout a process, the concentrations will be held, we can say that it will be constant. So the transfer or the diffusion rate we can draw in a linear fashion. Suppose imagine this as a thin metal plate, and this pressure at this point is PA and this point is PB. Okay, since the condition is that PA is greater than PB, and we can see that the direction of diffusion happens in this way, since pressure is more at this corner. At a constant, that diffusion rate is happening, so it can be represented in this fashion. CA and CB represent the concentration of A and concentration at the side B. and XA is the position of the A and XB is another position in the B side. Now with more deep into this one, like when the concentration C is plotted against the position or the distance with the solid X, the resulting curve is termed as concentration profile. So this one is a concentration profile, concentration versus the displacement. So the slope of that particular concentration gradient can be written as dC by dx. Okay, so this concentration gradient, which concentration is expressed in the terms of the mass of diffusing species per unit volume of the solid. So this concentration in general is termed as kilogram per meter cube or gram per centimeter. So here comes the Fick's law, first law. Fick's first law is very much significant, which indicates that the flux J is proportional to the concentration gradient. Okay, we take the concentration gradient, the flux will be proportional to this concentration gradient, and that proportionality constant is termed as D, which is termed as the diffusion coefficient, and it is expressed as the meter square per second. And here we can see that there is a negative sign, and this negative sign indicates that the concentration or the movement of the atom happening from a higher concentration towards a lower concentration. So this is a steady state diffusion, and here is a problem, and let us see this problem. A plate of iron is exposed to a carburizing, that means a carbon rich atmosphere on one side. So while doing this problem, I recommend everyone to imagine this figure. Okay, one side is this one and another side is this one. Okay, so carburizing atmosphere on one side and decarburizing atmosphere on the another side, so at 700 degrees centigrade. So if a condition of steady state is achieved, calculate the diffusion flux of carbon through the plate if the concentration of the carbon at position of 5 and 10 mm. Okay, beneath the carburizing surface are 1.2 and 0.8 kilogram per meter cube. So here this CA and CA and CB is given as 1.2 and 0.8 kilogram per meter square, and the diffusion coefficient D is taken as 3 into 10 raised to minus 11 meters square per second. So like applying the Fick's first law, this is minus D into CA minus CB by XA minus XB. So the values everything are here. XA is here, XB is here, CA, CB and D is there, and on solving we will get the diffusion flux J. Okay, now moving to the next part, that is the non-steady diffusion. Okay, we have seen the steady state diffusion, but in most practical cases, in almost all practical cases, we cannot achieve this steady state diffusion. It is a theoretical it is just for the theoretical purpose. For in practical cases, we can have the non-steady state, because the diffusion flux is, we cannot say it can vary with the concentration gradient at some point of time. Okay, so the real figures, for the experimental figures, it look like this. Concentration of the diffusing species on the y-axis and the distance is on the x-axis. We will not get a straight line, rather we will get a curved line like this. As the time changes, this will also vary. So for explaining this, we cannot use the initial Fick's first law. So in these cases we use a second equation, which is known as Fick's second law. Okay, in this one, the dou C by dou T is equal to D by dou square C by dou X square. Here you can see that the concentration varies. It shows a relationship between the concentrations in terms of both position, that X represent the position and T represent the time. Okay, as mentioned before here, like since it's a practical case, in order to solve certain conditions, we need to take some assumptions. So the assumptions are: before diffusion, any of the diffusing solute atoms in the solid are uniformly distributed with the concentration of C0. So the initial concentration, we will say it as a C0, C0. The value of the x, which is the distance at the surface, is 0 and increase with the distance to the solids. The value of the x at any surface will be, suppose if this is taken as a surface, here the value of x is 0, and as depth increases, the value of the x also increases. The time is taken to be 0 the instant before diffusing the process begins. So initially the time is 0 and time increases 0 when once diffusion starts, time starts to count. Okay, so in general it can be represented like this. For t is equal to 0, at when before diffusion the time, the c is equal to 0, c is equal to c0 at any point. Okay, and from 0, x is equal to 0 to infinity. For t greater than 0, that means when time starts, c is equal to cs for x is equal to 0, and at when at infinity or from other values c will be equal to 0. So an application of these boundary conditions to the fixed second law, that means this law, like applying and on applying, and there is some mathematical calculation is there, and we are not going behind those things, and we will get such an expression. Okay, just by heart this expression, and which indicates that cx minus c0 by cs minus c0 is equal to 1 minus error function of x by 2. And ERF means an error function. This is given here. Okay, and Cx represents the concentration at the depth x. Okay, and Cs and all you will get it from here, which I have already explained. Okay, now let us see one problem. Okay, consider such alloy that initially has a uniform carbon concentration of 0.25 weight percentage and is to be treated at 950 degree centigrade. If the concentration of the carbon at the surface is suddenly brought to and maintained at 1.2 weight percent, how long will it take to achieve carbon content of 0.8 weight percentage at a position 0.5 mm below the surface? So the x value of the x is given as 0.5 and other values like 0.25 weight percentage. So the uniform concentration, that means the initial uniform concentration C0 is 0.25 and Cs is that 1.2 weight percentage, and Cx is 0.8 weight percentage is given. So the diffusion coefficient of the current, that is D, is also given, assuming it is a steel piece. So all the data is given here. We need to find out. Okay, find out the time, and here like applying it to the above equation, we will get substituting it, we will get like this. So on solving, we will get the value as 0.421, which is the error function. This one. So this error function, this one, we will get the value as this one. So here we have got a table, and the table we have the values of 0.35 as this value and 0.4 as this value. That means our error function value will come in between these two values. So we need to do some interpolation. Okay, in this, by doing this interpolation as shown here, we will get the value of the Z. Okay, this Z is this one. Okay, that means the error function upon this Z will give this value. Okay, so on substituting this, we will get a value for the t of the time as this much seconds. Okay, which is equal to 7.1 hours. So after this much hours, this concentration will be attained at that particular minute. So that's all for this video, and thank you for the attention.